All right, ready for another day of computer systems?
Sure.
Now that you've turned in your big milestone project, I collected them and have the documents. I haven't tested them yet, but anyway. All right, so now now that you've done that, breathe a sigh of relief, and we will continue on, sort of like in parallel, back to chapter 6 on how to translate, how the compiler translates from C++ to assembly language. All right, so the last thing that we did, we've done, now what have we done so far? We've done control structures, like if statements, while loops, yeah? For statements, we see how those work. And then last thing that we learned was how to pass call by value parameters with void functions, right? And remember, there's a difference as depending on whether the parameter that the actual parameter you're passing is a global or a local. But we saw how it is a pretty minor difference. Globals, where are globals? What's the C++ memory model? The first one is what?
Global variables.
Global variables stored. Fixed location in memory.
Local
variables. Runtime stack. Dynamically allocated variables on the heap. So, let me see, why did I have you review that? Oh, right, and so the two kinds of variables that we were able to pass on to the runtime stack were the globals and the locals, right? The only difference is when you have locals, you got to get the value using stack relative addressing and so on. All right, so now what we're going to do today is we're going to see how to call a non-void function in C++. So I don't have to ask you this because it's right up here on the slide. What are the four things that happen? You got to push. The additional thing that we have to do now that we didn't do before is we have to deal with storage for the return value. Are you with me? And so that's the first thing that has to happen is you push storage for the return value, and then you push the actual parameters and what instruction, and then you have to push the return address, and what instruction pushes the return address? Call. And then we push storage for the local variables. Right? So the example that we're going to use is this example that we actually reviewed in the C++ section. I think, as I recall, earlier on in this semester, didn't you have to draw the runtime stack for this? This is the binomial coefficient function. Do you remember this exercise? And remember, I don't know if you remember at the time, but we were saying, all right, now you got to know what order and where they are, okay? Because why? Because now we're going to see how what is implicit in C++ has to become explicit at the assembly language level. Because what is abstraction? Hiding detail. And so now the compiler has to fill in all those details that are invisible at the higher level language level, right? Are we good? So here is our old friend, the binomial coefficient, and we've already seen this code before, so everybody understands how it works. And you've even sketched the runtime stack for that. Are we good? All right. Well, I hope I have more pins. Is this pin going to work? Oh, this is a good pin. Okay, so shall we do it? Good deal. All right. Now, maybe we should do the main. Do we have any locals or globals in main?
No.
We actually don't have any, right? So maybe we should do main first.
Branch to main.
Yeah. Well, okay. We'll start branch to main. Now, actually, maybe what we should do is, let's do main way over here, because I think this is going to be pretty kind of involved. All right, so let's come over here to main. So here is main. All right, so now can we whip out main pretty quickly here? What do we see over there for main?
String output.
Stro. Message 1. Addressing for stro is always direct. Okay? And then?
And then we're gonna have to.
Oh, and now what do we have? Ooh, this is interesting. How are we going to do this? We have a function call, but the function call is in the middle of the cout. Are you with me? Mm-hmm. So now, when we call that function, what's it going to do? It's going to return the return value at that allocated, at that allocated spot, right? Mm-hmm. So what we have to do now is call the function. Now, maybe what we should do is, let's come over here and let's draw a picture of the runtime stack. So now, what's the runtime stack going to look like in this case? What's the first thing that's going to be on the run? Now we have to review your homework exercise from the beginning of the semester. So what's the first thing that's going to be?
Storage for the return value?
Yes. So here is retval. Okay. Then what?
And then we're gonna have the actual parameters. So
Yeah, the parameters. And so what are the parameters in order? We have to label them with the formal, right? N and K. Do you remember doing this? Mm-hmm. N and K. All right. Then what?
then the return address.
Then the return address. Okay. Then what?
There's no local range.
Yeah, I think there are.
Y1 and Y2.
Oh, are we doing the other? Yeah, Y1, Y2.
Y1 and Y2. So here is Y1, and here is Y2. So this is what the stack is going to look like. This is one stack frame, right? Okay, so now where are we at this point? SP is here. Are you with me? Oh, yeah. So, actually, oh, shoot. I'm wondering how we should handle this retval.
That's a good question.
Because, well,
At the return.
we have to set up, here's what we have to do. We're going to have to, what are we calling bin coefficient with? We're calling it with what?
N and K.
3 and 1. So where do we have to put and we need to put the 3 here, right, and the 1 here. And then we have to sub SP to get up here and then do the call.
Yeah.
Now, is everybody with me on that?
Yeah.
Okay, so how do we put the 3 here? Because SP is here, right?
So we have
So-
to load the accumulator with the 3 first.
Yeah, so we have to load it, exactly, that is correct. So load accumulator 3, addressing immediate,
And then store the accumulator
and then store accumulator
at -2.
at -2 stack relative. So that will put the 3 in here. Is everybody good on that? And then what?
Load accumulator again.
Load accumulator 1, immediate, store accumulator -4 stack relative. Okay, so that puts those there. But now, when we sub SP, we want to sub SP how much? So this is this is 1, 2, oh no, so well we have to sub SP 2, 4, 6, right. So here is sub SP 6, addressing immediate. But now what are we allocating here?
We're allocating
Here it's
Retval and
allocate. Retval and and K. But now see, I'm a little, oh, we need pounds, right? Allocate pound ret val, pound n, and pound k. But now, wait a minute. Ret val n and k, you see, what does the assembler need for ret val n and k? These have to refer back to symbols, right? And where do we put these symbols? They're going to be at the beginning of our thing. So let's go ahead and take care of that. Now when we are executing the bin coefficient function, SP will be here.
Right.
Now, is that clear?
Mm-hmm.
So therefore, what will the values of, so here whenever we are referring to ret val n and k, what values are we referring to? SP plus what? 2, 4, 6, 8. No, not negative.
Positive 6 negative.
Oh,
I think, so let's come over here and let's take care of this right now. So here we have, so what was ret val? And now, so what does ret val do?
Wait, 8.
Dot equate.
Or is that one 10?
Isn't it 10?
Yeah, that one's 10.
This one's 10, I think, right? And then
And
n
wait, 8.
dot equate to 8.
Okay.
K dot equate to 6. And actually, while we're here, we might as well, no, return address we don't have to deal with.
Y1 and Y2.
And then Y1, let's go ahead and do Y1 and Y2 while we're here. This is dot equate, will equate to 2, and Y2 will dot equate to 0. And over here, we have to say how we want to display the ret val, right? Isn't here where we put the format trace tags?
Yeah.
So what kind of a quantity is ret val?
Pound 2D, but I don't.
It's an integer, isn't it?
Yeah.
The value, the binomial coefficient, these are integers. So here what we want to do is, this is going to be a, whatever you want to put in English here, but then the trace tag will be pound to D. Now how about N? Is that going to be an integer?
Yeah, they should all be pound 2D.
Well, be careful here.
K is also pound 2D.
Oh, right, yeah, we don't have to be careful. They're all pound 2Ds. Pound 2D, pound 2D, pound 2D. I was thinking about the return address, but that's automatically done in hex by the system. Okay, so here we did sub SP, 6 immediate, and then what do we do?
Now we call.
Now and when we did the sub SP, that makes the SPB go from here up to here, right?
Right.
And then when we do call, but now what are we calling? Well, we're going to have a
Bin coefficient.
bin coefficient. Okay, so.
Lowercase b.
And that will put SP up to here. And then, so now over here is here's our bin coefficient, right? And now this bin coefficient, so now what does bin coefficient have to do?
7.
How many?
4.
Sub SP for addressing mode? Immediate. And here what are we doing? We are allocating, so what are we allocating? What,
Y1 and Y2.
Go
Is
ahead.
it pointing to K or to ret address? Because I thought thought we subtracted 6. So does that mean?
The call, we subtracted 6 to get it to here, the call got it to here, and we subtract 4 to get it to here. Are we good?
Yeah.
Okay, so now we are finally up to here. Okay, so, and here we allocate y1 and y2. Now, I guess it's a toss-up here. Let's come over here. Let's go ahead and finish this off. Now, after we well, okay, it's a toss-up whether we want to, which one do you want to write first, but.
This one's gonna be harder.
Well, okay, let's finish this. I keep oscillating back and forth here. All right, so now after we call this, here we did sub SP, that got us up to here, and boom, here. So now when we get back, I was about ready to change my mind again, but I don't want to do it. So when we get back, you know, ret 4 will take us to here and to here. So how do we, here we sub SP here, right? So now what we have to do is we have to add SP. 6 immediate, and this is deallocate. And what are we deallocating? K, N, and ret val, right? Pound K, pound N, pound ret val. But now here, you guys, here's the thing. After we do add SP, after that function has been called, where will SP be? It will be right here. Are you with me?
Yes.
And furthermore, where will be the value that got returned?
-2.
That will be here, is correct. Okay, so the value that gets returned will be here, which is at -2. So how do we finish off the main program? Yeah, decimal output from where?
-2.
Deso, -2, stack relative, excellente. I can see that you are with me. After which, do we do anything else?
We just did Caro, bash n.
And then Caro, quote, bash n, immediate, and then stop, and, oh, we need message, yeah. And then, what is this, dot ASCII, quote, blah, 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 and then dot end, right?
And we're still not worrying about return 0.
And we're still not worried about return 0. And we have gotten all the way down, there's no locals to deallocate before we quit. So are we good there? Okay, so now the question is, how do we do the function call? Or we just did the function call. Now how do we, and we allocated the variables here, the locals here. And so now what kind of a function is this? It's recursive.
Yeah.
But there's nothing, I mean, everything just, there's nothing special about that we have to do because it's recursive. We just call it constructing the runtime stack the way we always do, right? So there's nothing new here. Only thing is, you know, we got to make sure about this ret val. See, it returns y1 plus y2. So we've got to make sure that we do these returns correctly. All right, so let's see how to do this. So first, so what do we have here? If k equals 0 or n equals k. Oh, holy moly, how are we going to do that? Well,
That's the first one.
so what? Load accumulator what?
Do you want to do an if symbol first? Or not?
Well, yeah, sure, why not? For documentation.
Load the accumulator was 0.
So load accumulator 0. No, we want to do them in order. So if we're going to do k and 0, let's do k and then 0, yeah.
So load accumulator.
K.
And is that stack relative?
Good question. Load accumulator k, well,
Yeah.
yeah, why not? Because it's on the runtime stack, right?
Yeah.
Okay, so load accumulator k, and then what?
And then compare accumulator.
Yeah, compare accumulator 0 immediate. Now, I think this is, I think,
If you just did CPA by itself.
yeah, no, I think if you just load accumulator, I think load accumulator we'll set, I mean, you want to optimize here?
Yeah, we
Yeah, just
don't
take
need
it out.
that.
Yeah.
Because it always.
Because it, yeah, because it sets the n and the z bits with the load.
Right.
All right, so we can optimize here a little bit. Okay, so now, but now, what do we branch? Now, here's a compound, ooh, and we have short circuit evaluation. So what?
If this is false.
When do we know that we don't when do we not have to do the next test?
If it's true.
If k equals 0,
If it's true,
And we
if it's
don't
true.
do the next time.
then we don't,
So branch if
So
equal to.
branch.
so we branch
VRE?
if equal to the if,
Like statement.
yeah. I'll tell you what, let's do. Let's not put the if here. Let's do branch if equal to if, and we'll have the if
Okay.
part down here. You see what I mean?
And then we want to.
And now, if it's not equal, then we have to test with n equals k. So how do we do this?
So load accumulator n.
Load accumulator n,
Stack relative.
stack relative.
Take a Warford? Is
Yes,
branch if equal to, does that have a Q?
yes it does. And then compare accumulator
Okay.
k stack relative. And now, if this is true,
So we branch.
if this is equal, we do the if here. If it's not equal, we have to do the else. So we branch if not equal. Branch if not equal to the else. Are you with me? And then we'll use if for this part. All right? Is everybody clear? And now what happens? Oh, and now here you guys. How do we return 1?
We load accumulator.
We load accumulator 1. So check this out. We load accumulator 1 immediate,
And store accumulator.
and then we store accumulator ret val.
Stack,
Ret val, stack relative. And now how do we, this says return. Right there it says return.
So add
So we have to return at this point. So how do we return?
return 4. Ret 4.
It's ret 4. Now let's go over here. Why is it ret 4? Because, yeah, right, because we are here. And ret 4 will take us down to here and then return to this return address. Are we good? So this is ret 4,
Which is unary.
which is unary. And now, over here, we have the what? The else part, right? Okay, so, ooh, now what do we, now what do we have to do?
Call it again.
We have to call, yeah, now we have to make a recursive call. So how would we make this recursive call? Well,
Don't we have to change n first?
we do it, we just make the call like we make the call. What do we have to do first?
Change n?
Yeah, what do we push? The first parameter is what?
N minus 1.
N minus 1. So how do you do, so how do we have to compute n minus 1? So how
Load
do,
accumulator n.
load accumulator n. Load accumulator n,
Stack relative.
stack relative. Subaccumulator 1, immediate. Are we good? And now store accumulator, but now the question is, where do we store accumulator? Well, where is n going to be? Well, you know, it's the same thing as we did here. Boom, here. Only here it's another one on top of that. We are building a new stack frame.
Okay, so we just say negative again? Same exact
It's the same exact process, yeah.
negative 2?
Negative 2. Now, does everybody see how that works? Because we're building a new stack frame on top of the stack frame. That's how recursion works, right?
Cool.
Okay, so store accumulator negative 2, addressing,
Stack relative.
stack relative. So there's the n minus 1, then what?
Then we have to call.
No, there's another parameter.
Oh, we can, okay, so we.
K, so what?
Load accumulator, okay.
So load accumulator K, addressing, stack Store accumulator what?
Okay.
-4.
I mean, -4.
-4
Stack.
stack. And now what?
Now we can call. Then call it.
No, we got to,
We have to sub SP.
we have to sub SP, but now how much do we sub SP by?
6 again.
6 again. Yeah, did you have a question there?
This reallocates again. Allocate.
Yeah, and we have to say allocate. Did you have a question?
How? Never mind.
Okay, rep val n and k.
That's at 0.
It's at 0.
So this will just replace the values on the stack.
I would think minusing 2 would be the first thing in that. Is that right?
Because
Yeah.
we're not adding any new things to this.
0.
Well, what we're doing here, look,
SP's pointing.
what we're doing is, this is the stack frame of the call from the main program, right?
Right.
And what we're doing is we're building, you know, you remember how you did those sketches in that exercise?
Yeah.
That was n, and you know, this is k, and et cetera.
So, but it uses the same space,
Space.
like
The same stack.
the same stack. Like the dot equates it remain exactly the same.
They will because once we sub SP 6 to get it up to here, and then do the call to get up here, and then do the 4 to get up there, at that point, those n and k's, those offsets will be the same offsets. Are you with me?
No, yeah, it's perfect.
The stack pointer will be up there, and
That's just really smart.
it is smart. Well, this is how the hardware does those details that were hidden at the lower level of abstraction. Now, did you have a question?
No, I'll look at it.
No, ask away.
Well, I'm just confused at the start where the stack pointer's pointing. Because we said we said store accumulator -2. But I'm confused about why that wouldn't be pointing to rep val. If you
She's talking about when we start the program.
Oh, maybe we made a mistake.
I don't think so. Because isn't red val technically 0?
Oh, no, hold on. Did we make a mistake here? You know, you might have caught... Yeah, actually, did we make an error here? You guys, check it out here. SP is here, right?
Mm-hmm.
We did make a mistake.
Is this supposed to be -4?
I think it is. I think this should be -2, -4. N should be at -4, right? Ret val will be at -2. N would be at -4, and K would be at -6. Oh, I think we made a mistake.
A quick fix.
What's at 0?
0's
Oh, no, well, that's,
0 is your stack point.
yes, yeah, the stack pointer is not pointing to an element at the beginning, right?
Yeah.
Yeah, ooh, boy, that was, I hope people didn't turn off the
Video yet?
video and then not get this. So this is 4 and this is 6. That was a quick fix, huh? And so now we have to quick fix this too. Well, see, you should have spoken up. Otherwise we would have left this error.
I thought I was probably wrong.
Well, see, that's what you get for not having confidence. All right, so now, okay, so now what?
Sorry. Add SP? No, sorry. Call.
Okay, so sub SP, and now we do call, and now what do we call?
Bin coefficient.
Yeah, so it call itself here. So call. I like doing this on the board because we can think through as we're doing it. Okay, so and then what?
Add SP. 6. Or would we?
But now we have to make an.
We just have to load accumulator with.
Oh, so yeah, sub
add
SP,
SP.
call, and then call, and then when it calls itself recursively, that will complete that and it will do its thing. And so now we
Add SP.
add SP, how much?
6 immediate.
Add SP, 6 immediate. But now, you guys, comes a big question. Now, isn't this a great example? Because look, what does it say? What does it say we do with bin coefficient?
So we just store the
We set
return
Y1 to
value
it.
in one.
We set Y1 to that.
So load accumulator.
So we load accumulator, but now here we go. We load accumulator what?
-2.
-2
Stack relative.
stack relative. Because, and why is that? That's because
That's where the ret val is.
that's where the ret val is. So here, when we come back, stack pointer will be here. Oh, shucks, another mistake.
You forgot to put the ret val.
I forgot to put the ret val. This should be ret val n and k. Okay, so ret val n, etc.
Perfect.
Okay, so load accumulator negative 2s, stack relative, and then store it into what?
Y1.
Store accumulator into y1, stack relative.
Now I have to do the same thing.
Now we have to do the same thing for the next call.
And so we do another stack frame?
Right, well, yeah, we have to do another call, right. So now what would it be? Should we, do you want to just, can you see it?
Yeah, it's the same,
It's the same thing, right?
except you have to load accumulator
It's,
K.
this time it's load accumulator, well, all right.
Well,
Let's do it quickly.
Well, n is already is in the right spot, isn't it?
It's a new stack frame.
No, yeah, this is a whole new stack
But
frame.
isn't the space still? It's
But it's gonna be the same.
it's going to be the same
Yeah.
value.
Well, let's not, that optimizing, remembering what was in the former, really?
You should.
Why should?
Because you pop it.
Why wouldn't?
We never change it?
The K.
Yeah, okay, well, now that would be, that would be a gnarly optimization to realize. I didn't even think about that before.
Do we have to change K?
But let's not optimize.
Okay.
So load
load
accumulator
it
N.
Actually, it would be interesting to take our solution and optimize it and see, make sure it still worked. Okay, so anyway, load accumulator what?
N stack relative?
N stack relative.
Sub A.
Yeah.
Subtract
accumulator. 1.
Oh, because it's n minus 1?
Yeah.
I see. Subtract accumulator, 1,
Immediate.
immediate,
Store accumulator negative 4.
store accumulator, negative 4,
Stack relative.
stack relative,
Load accumulator
load accumulator,
K.
k,
Stack relative.
stack relative,
Sub A. Sub accumulator
sub accumulator,
1.
1,
Immediate.
immediate,
And store accumulator.
store accumulator,
Negative 6.
negative 6,
Stack relative.
stack relative,
And sub SP.
and then sub SP how much?
6.
Sub SP 6, immediate,
Which is allocating again.
which is allocating.
We forgot to deallocate above.
Oh, we forgot to deallocate above,
Right there.
add SP, pound K, pound N, pound ret val. Are we good? And here we're allocating the same thing. We could copy paste.
Yeah.
Too bad I can't do that on the board. You know, in these futuristic science fiction movies, I could take this and go and have all this stuff move around and press the duplicate and have it go down here,
Dot, dot, dot.
allocate. Yeah, let's do dot, dot, dot. I'm ready to do dot, dot, dot. Ret val, pound N, pound K, all right? So it sounds like you're all with me. Dot, 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 dot. So, drum roll, you want to check to see if our...
To set the return value to y1 plus.
Oh, you know, we should.
We can just do it right here in this empty space to the right.
Let's think about how we do return y1 plus y2.
Store accumulator.
So
Y1,
load accumulator y1,
stack relative.
stack relative.
And then add accumulator.
Add accumulator y2, stack relative.
And then
Store accumulator
into ret.
ret val.
Ret val. Perfect.
Okay.
Is that good? Does everybody see? Okay, look, you guys, here it is. Now, did we do this? First of all, are all of our equates correct?
Yes.
108,620.
108,620 for ret val and k y1 and y2. Gesundheit. And then sub SP4 for allocating y1 and y2. And then, are these all correct? Load accumulator, branch equal.
Oh, then.
Did we do it?
A little different.
A little bit different? What did they, Oh, was the branching?
We had branching.
oh, we had if, we just, oh, I see, I had if and then. Yeah, okay,
That makes
well,
sense as far as-
if, then, else, yeah. Are we good? But anyways, And now, let me see, what is this? Is this our, this is, yeah, this is all this code for the calling the binomial coefficient. Is it correct? Check me out. Check us out.
Why
So
use
those
symbols?
the symbols were useless. They're just so you can see.
RA2 and RA3.
They don't do anything.
Yeah.
Oh, we have some symbols here? What?
Those are the return addresses.
Oh, you know what that is? That's, I put these comments here on the C++ code,
Okay.
and that's for to document this RA1, RA2, and RA3. Those were, I don't know if you remember, but remember we had you actually put those
We did.
return address ones in the runtime stacks just so you could comment it. But now we know what these return addresses are. You know, they are going to be these hex values, yeah? So is everybody good for that? And so that's just, yeah, those are, those symbols are never used in the program, so that's just for documentation. And then there it is, and here's the runtime stack. And you want to see the coolest demo? This is, actually, this example, we used this when we were debugging the, you know, the PEP8 simulator and assembler. Man, I saw this thing run a bazillion times when we were writing the, because this was the canonical test case. All right, so so let's do a demo. Okay, so here's our demo. We go to this help system. We look at figure 6.25. And here is, over here is the C++ program. Look familiar? And here's all that code that's translated. We do copy to source, and here it is in the source. And we build it, and boom, there's the object code. Here's a nice listing, program listing. And we start debugging. Now, watch this, you guys. We're going to single step through. First, we'll branch to main. Yeah? String output. So you see over here in the output, there's the bind coefficient 3.1. All right, and now let's single step through this. So first we're going to load accumulator with the 3. So check out the accumulator. It's 3, right? Up here. There's the 3. Okay. So load accumulator, and then store accumulator, -4 stack relative. Load accumulator 1, accumulator change to 1, store accumulator -6. And now when we sub SB6, we push retval, N, and K. Boom. Is that slick? And now you guys, when we call, I want you to predict what value is going to be in this return address cell.
The next instruction. Like,
What address will be in that return address cell?
7A.
7A is correct. Are we good? And now we're going to sub SP, and now when we do this sub SP, there's the Y1 and the Y2, and there's our stack frame. Is that slick? Now does K equal 0? Did it?
No.
No, it doesn't.
No, it didn't.
So it branches right away.
Well, it doesn't.
No, so now we test. So now does N equal K? Okay, so we branch, so now do we branch?
No.
Yeah, we do. Well, yeah, we do. Okay, and so now what do we do? -1, okay, and then store that, and then load this, and then store it. And now when we sub SP, what's going to happen? Boom, there it is on top there. And now you guys, what can you predict what's going to be in this ret address? 0, what is it now? 2E, right? 3.1. Okay? Does everybody see how that worked? And now, here we go. Boom, 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 boom. Another stack frame on top, and then that stack frame goes down. Another one goes up. That one goes down. That one goes down. another one goes up, that one goes down, and boom. And what do we have? 3. Is that slick? All right, so that was our demo. And now what we're going to do, the next thing that we're going to learn how to do is how to do, now what parameter, how are these parameters called? Here, let's go back and look at the C++. How are these, whenever it says int, binomial coefficient, int, n, those are called by value. So what do we have to do next?
Call by reference.
Call by reference.
This might finally make sense.
Yeah. Actually, you know what? We only have maybe 5 more minutes. Maybe what we'll do, well, no, we can introduce it. We will introduce the concept. But let me just mention then, what you have due for Friday is an example of a call by value that returns an integer. It's actually a multiplication algorithm that's done by shifting and adding. Have you noticed that there's no multiply instruction in PEP 8?
Yeah.
Sure.
Yeah, so how would you multiply? How would you multiply 2 numbers? Yeah, well, you have to do it in a loop by shifting and adding. And so there's a really interesting algorithm. If you look at the code, the algorithm is given as a C++ program in the exercise, but if you examine that code, you should actually think about, instead of just translating it, you can just translate it rote the same way we did this, but you should think about how it works. It's a really slick application. And it's how you would do this. It's how you do multiply when you don't have a hardware multiply unit. It's how to multiply in software. Okay, and then guess what the other one is? No. The other there's 2 problems that are due Thursday, and guess what the other one is? Do you remember? Not only did we review this binomial coefficient recursive thing, but what's the recursion example that we always like to program whenever we're learning about recursion?
Fibonacci.
No.
Towers of Hanoi.
Yeah, do you remember you did Towers of Hanoi in C++ at the beginning of the semester?
Oh,
Do you remember that? Do you still have that?
yeah.
You should still have that, and then that's what you have to translate.
That was beginning of this.
Are you with me? So you go back to that C++ program where you did Towers of Hanoi. And by the way, you might want to, some people were pretty fancy with how they did things. You might want to make it very short, as short as possible, because you're going to have to translate it. Okay? So hand in your C++ program of Towers of Hanoi together with your translation of it in PEP 8 assembly language.
So it has to output which moves to move, like.
Yeah, and it's important that you have the output occur, that you have the parameters occur in, I'm sorry, that you have the input. The thing that's super important is that you have the input exactly like as specified in the exercise, because I have a script that tests your programs, and if you input if you input them in a different order, then it messes up my grading software, my grading script. So anyway, yeah? Is everybody clear on that?
Mm-hmm.
What's due? And I think that's a void. I think that's a void one.
Do we have to do preconditions or anything, like if they put in the wrong?
You know what? That would just make it longer than necessary. And I think a lot of people, yeah, I remember, people, when you did that, you did lots of nice error checking, which is good from a software engineering point. But if you want to minimize how you translate your code, why don't you just get rid of all that and just assume that the input's going to be correct.
Okay.
Okay? And with that, we'll call it quits. See you next time.